move on to a bit of work on axiomatic derivations of that one. So we've already seen how to generalize the preparations and the measurements. So instead of representing just by vectors in Hilbert space and projection value measures, the most general sort of preparation procedure is represented by a density operator, and the most general sort of measurement is represented by a positive operator value measure. And now we're going to talk about transformations that can't be represented by unitary maps, but have to be represented by something more general. So I'll start again with the same sort of simple example that breaks the mold. A transformation procedure, remember, is some device which intervenes between a preparation procedure and a measurement procedure. Look, this one here, so it has an input port and an output port. And so now I imagine an effective transformation wherein you choose to do one or another unitary at random with some probabilities. Okay, so if your goal is to predict the outcomes of some measurement that comes after the transformation device for some particular preparation procedure, so suppose you know that this guy's associated with rho, this guy's associated with some POVM, and you want to know, well, what should I predict about K given that there's this intervening transformation here? So you just need to do the calculation. So you say, well, what's the probability of K? It's the probability of K given I, where I is an index that labels which unitary you've done, times the probability that that unitary was actually done. And probability of K given I is just given by the quantum formula. So it's the Born rule, where you've evolved rho forward with the ith unitary, and then you've taken the trace with the POVM element. And so now it's the same trick. You move the sum inside the trace, you move the PIs inside the trace, and you get an expression like this. So I can write that as sum map, which I'll call script T, acting on rho times EK traced, gives you the probabilities for these outcomes. And that map is defined as a convex sum of these unitaries acting by conjugation on the density operator. And typically, such a map, if it's non-trivial, if the non-trivial sum of different unitaries is not equivalent to some particular unitary. In general, whereas a unitary takes a pure state to a pure state, so if rho happens to be just a projector onto a vector, you act a unitary on it, you'll just get a projector onto some other vector. This sort of map tends to decrease the purity of your state. If you start with the projector onto psi, and all the different UIs map you to different states, psi 1, psi 2, psi 3, then at the end what you've got is a mixture of these different states, and that's not a pure state. So these sorts of maps tend to reduce the purity of your state. You can think of them as adding noise to the system. So your ignorance of which unitary was applied then decreases your ability to make predictions about future measurements. So the more you mix, the less predictability you have. And if you have certain sums of unitaries correspond to what's called the completely depolarizing channel, which takes in every state, every pure state, and returns you the completely mixed state, which is the state where you have the least knowledge and you can make no predictions about any outcomes. So a transformation can, like this one, can decrease the purity where the unitary cannot. There's a second sort of way of approaching generalized transformations, and this is just in parallel what we saw with the preparations and the measurements. I can take my system in, I can then interact it unitarily with some other system, an ancilla system, which I've prepared in some density operator tau. And then I could throw away the ancilla system and just let the system come out of the box. So this is a model of open system dynamics. I'm interested in this system here, but I know that it's not isolated. It's coupled to this ancilla system. And the question is, what kinds of dynamics can arise for the system if I allow arbitrary sorts of couplings here, arbitrary initial states for the ancilla, and arbitrary possibilities for the dimension of the Hilbert space of that ancilla. All right, well, let's find the general expression. So again, you just ask, well, what would I get? What would I predict for the outcomes here, given this transformation. And this is the formula. So first I analyze it as if this is a measurement on system and ancilla. So remember we had a discussion last time that if I'm not getting any information about this system, I model that by the measurement which just has one element in its POGAM, which is the identity operator. So thinking of this as a measurement on system and ancilla, it's just this POGAM. It's non-trivial only on the system and identity on the ancilla. And of course, the preparation of system and ancilla is just rho tensor tau. It's a product state. And I need to throw in this unitary that couples the system and the ancilla to evolve forward the state. This might have the effect of entangling these two guys, or at least correlating them. And then I just trace over the system and the ancilla to get the probabilities for those outcomes. This is just another application of the standard Born rule. And now I start just doing some algebraic manipulations. I move the trace over A through this operator that depends defined on the S over space. So I get the trace over A of this guy here. And I can think of that now as some effective map on rho. Because remember, if this thing here is an operator on S and A, I'm taking the partial trace over A, so what's left over is an operator on S. So this map here takes me from an operator on S to another operator on S. That's what I'm looking for. And so the definition of this map T, in this case, is just given by this expression. Okay, so that's two examples of transformations that go beyond unitaries. I guess I didn't say it explicitly, but typically this sort of evolution cannot be simulated by a unitary. Another question is, well, what sorts of properties do these maps have? So I've given you a couple of examples of why we know we have to go beyond unitaries, but I haven't told you exactly what the mathematical properties of these maps are. I already mentioned this, that this is the paradigm for open system dynamics. I think it came up on the first day. Somebody was asking, how do we model open system dynamics in quantum theory? And this is the answer. It's using these sorts of maps. This is also the paradigm for decoherence. So as I said in the previous slide, those mixtures of unitaries tend to take pure states to mixed states. So do these kinds of evolutions. When I have a system and I couple it to an ancilla in some non-trivial way, if the state that I fed in for the system was pure, what comes out tends to be mixed. You can think of it this way, that purity for a system state means a high degree of predictability about the outcomes of certain future measurements. And if I couple the system to the ancilla, then not having access to that ancilla means I've lost information, right? So by not analyzing the ancilla, I basically let information leak out of the system, and I'm ignoring it, and my predictability goes down. And so typically, as we transition from pure states to mixed states, then relative, let's say I'm interested in some basis of which my initial state was an eigenstate, or some operator, z-spin. My initial state is an eigenstate of z-spin. If I interact with the environment, it tends to become a mixture of different z-spin eigenstates. It tends to become mixed, and so it loses coherence in the z-spin basis. In any case, this decoherence usually arises by systems interacting with their environments. Oh, I have one third example before I give you the mathematical properties of these sorts of transformations. So here I'm imagining a measurement device, the type that produces a system after it's done. And I'm imagining that this device is associated with some projection value measure. But now the idea is that you don't register the outcome. So this is a black box, and you don't get the outcome of this measurement coming out of the black box. So from your perspective, you know the measurement has happened inside, but you don't know which outcome occurs. In that case, well, if you just looked at those textbook postulates, it would tell you that if the input to the box was a pure state, then you should just apply the projection postulate, and the output should be this guy with these probabilities. But now if you don't know, if you represent this in terms of density operators, that's the projector onto psi being mapped to, again, projector onto psi, now conjugated by these projections into the k eigenspace. Okay, that's if you knew the outcome k. This is the state you would write down. If you, sorry, this is just what you would write for an arbitrary density operator. It's the same formula as what I have here, but it's just for an arbitrary density operator. Whereas here it's for a particular pure state. So the reason I can go from this equation to this one is that I know that every density operator can be written as a sum of pure states. So and this is a linear expression in rho, so I can just infer this equation. Okay, so that's what the old textbook axioms tell us would be the state we should assign if we knew the outcome k. But of course, we don't know the outcome k. All we know is that we're going to get one of these states with probability pk given by the Born rule. And so we should average all those states with their weights. So if we don't know which outcomes occurred, we should assign this quantum state here coming out of this device. Yes?
How is it linear?
I'm sorry?
How is it linear in rho? It's also in the denominator?
Oh, I'm sorry. You're right. Only the numerator is linear in rho. So you can think of it this way. Imagine the transition from this state, not to the normalized final state, but to the unnormalized final state, just the numerator here. Then the transition from any rho to the unnormalized final state is given by this, and then this I just do to normalize. And of course here, because trace rho pi k is the probability for outcome k, these two terms cancel, and the overall transition is just this one. So that's sometimes called the non-selective measurement update rule. It's how you should update your description of the system if you know a measurement has happened, a projective measurement, but you don't know which outcomes occurred. You just sum over k of these guys. Okay, so that's yet another example of a kind of transformation. You know, this thing certainly satisfies the definition of transformation. It has it's deterministic, so you're not conditioning on any particular outcome. And it takes some preparation and defines an effective preparation. And it's typically the case that this thing will take pure states to mixed states. So for example, if this is a measurement of z spin, and I feed in, say, an x spin eigenstate, which is a superposition of z spins, this measurement will destroy the coherence among those z spin eigenstates and leave you with a mixture of the possibilities. Okay, so that's yet another example of the sort of map that we're interested in. Okay, now I'm going to move on to talk about what the properties of these maps are. So what properties should they have? So the idea here is I'm going to say, you know, can we identify all the properties that any such map should have, and then ask the question of whether we can achieve all such maps. So the first property is convex linearity. And what that says is, if the preparation procedure that comes before the transformation is known to be some rho I with probability Wi, then the output of the map should be the same mixture of the output of the map applied to each one of those density operators. And the idea is that if it really was, say, rho 1, then I would assign the output T of rho 1. That's just the transformation acting on that guy. And if it was rho 2, I would assign T of rho 2. And if I simply don't know which one it was, and I assign different probabilities for those guys, well then clearly, at the output, I'm just going to assign the same probabilities to all these different possible output states. So this has to be the state that I assign to the final state if I don't know what the initial state was. Does that make sense? So I'll call this property convex linearity. It's not quite linearity because these W's aren't arbitrary real coefficients. They're probability distributions, so they're positive and less than 1. Second property that you want is called the trace preserving property. So remember, every density operator has unit trace. That's part of ensuring that the probabilities you assign to different outcomes of a measurement sum to 1. And the final density operator after transformation should also be a valid density operator. Now this whole effective transformation here, this effective preparation with the original preparation and the transformation is another preparation procedure. So this also should have trace 1. And so T has to preserve the trace of all operators. Because the set of density operators actually are it's not so important, but they're a basis for the space of all operators. And therefore you can show that not just for the density operators, but any operator in the Hilbert space, this T is going to preserve the trace of that operator. And then a third property is that this T map should be positivity preserving. So again, it should take valid density operators to valid density operators. Valid density operators are positive operators. So for every positive row, T of rho should be positive. It just so happens that people call this property positivity rather than positivity preservingness. So when you see somebody talking about a map being positive, they really mean that it preserves positivity. And it turns out that that's not quite enough. There's one more property, a stronger kind of positivity that you need to assume. Because you could apply this map to a system S which is already entangled with some other system A. So imagine rho SA is some density operator on a composite. Maybe it's entangled. You can always apply T to S and do nothing to A. So this just denotes the identity map. And of course, if this guy is a valid density operator and T is a valid transformation, then it better be that this thing is also a valid density operator. So this thing should be positive when this is positive. And it turns out that positivity just on S is not enough to ensure this kind of positivity. So there exist maps that are positive, but not completely positive. That's the terminology people use to describe this property. T is completely positive on S if it has this property. An example of a map that's positive but not completely positive is the transpose map. So if I take this script T to be transposed on system S, then here it's called what's called the partial transpose. You have a system, an operator on S and A, but you're only transposing S. And it turns out the partial transpose is something that can take a positive operator to a non-positive operator. And so, although it satisfies this definition, it doesn't satisfy that one. And so we say it's not a valid transformation. And in fact, transpose typically is assumed to represent time reversal. So what this says is that there is no operation in your laboratory you can do that corresponds to just reversing the time, or maybe inverting the momentum of all the objects without changing their positions. It's not a valid transformation because if you acted it on half of an entangled state, what you would get out the other side wouldn't even be a density operator. It would have negative eigenvalues. And anytime you have an operator that has negative eigenvalues, and you're trying to use it to represent the preparation procedure, well, there's going to be some measurement that you're going to predict negative probabilities for some of the outcomes. And that doesn't make any sense. So actually, people use this fact about the transpose as actually a test of entanglement. So maybe I have a state that's quite complicated, and just looking at it, it's not clear to me whether it's entangled or not. I have a description of this state. So I can do the following test. I calculate the partial transpose on one of the systems, and I diagonalize the state that comes out, and I look if it has any negative eigenvalues. If it does, then I know that the original state was entangled. So this gap between positivity and complete positivity can actually be a tool, and they use it in entanglement theory. This business about testing for entangled states is really incidental to this discussion. I just thought I would mention it. Okay, so the idea is that if you have a map that has all these properties, then it'll certainly take valid density operators to valid density operators, even when you act it on one part of a whole system. So now you can ask, well, is it the case that all such maps are can be achieved by some experimental scheme. And it turns out that they can. I'm going to try to convince you of that. I mean, I'm not going to prove it, but I'm going to show you a representation theorem, which, again, I'm not going to prove, but which is going to make it plausible that everything I showed you up till now fits the mold of one of these sorts of maps. So, incidentally, these have a nice name. They're called completely positive trace-preserving linear maps. I haven't shown you explicitly, but once you have convex linearity, that actually implies linearity. And there's no shorthand. So people sometimes say CP, TP maps, completely positive trace-preserving. Yes?
So for the second property,
Yeah.
given that the argument is a specific kind of matrix, then is it a big leap to say that this transformation is trace preserving? Like it
Sorry,
sounds like
quick
it sounds,
question.
sorry, it sounds like
Yep.
the second property is you're saying that T is trace preserving only for density operators or for any operator?
So what I'm saying is it's trace-preserving for any operator.
Yeah. So
But it turns out that fact follows from it being trace-preserving for all density operators. So it might look as if it's a stronger statement to say it's trace-preserving for all operators, but actually it follows from it being trace-preserving for all density operators. And the reason is, if you give me any operator, I can write it as a linear sum of density operators. And I already know from up here that this T is a linear map. Later in the lecture, I'm actually going to talk a bit about how convex linearity implies linearity. And so if it's a linear map, and any operator can be written as a linear sum of density operators, well, then it's going to be trace preserving for any operator. Yes?
If convex linearity implies linearity,
Mhm.
and it seems linearity would imply convex linearity, then because the WI are simply weights,
Yep.
then why pick out convex linearity as anything special? It has
Well,
this physical significance.
Yeah, that's exactly it. Here I'm trying to say what properties should we demand of it. And convex linearity is clearly something we ought to demand. It basically says, if I have ignorance about the input, and I know that each of the inputs gets transformed to some particular output, then I have the same ignorance about those outputs that I had for the input. That just makes sense. What I know about the input should not influence how this device acts. So I start with that physical postulate, and then I get to the mathematical fact that this must be a linear map. Okay, good. So there's this nice representation theorem that says all maps which are completely positive, trace-preserving, and linear can be written in this form. So here, the AKs are just an arbitrary set of operators. They don't have to be positive. They don't even have to be Hermitian. Okay, so AK dagger need not be the same thing as AK. Just any set of operators at all. Except that they have to satisfy this condition. If I sum AK dagger, AK, I get it. So that's called the Krauss decomposition of the CP-TP map, or sometimes it's called the operator sum decomposition. Yes?
So you said this is a representation theorem.
Yep.
So what in general is a representation theorem, and what role do they play?
Well, a representation theorem, I'm not sure what you could say in general about it, but it's just, this is a statement about a mathematical expression for objects, these maps, that have the properties I've described. So this is, it's certainly not obvious that those properties I described in the last slide mean that you can write it this way. So there's a theorem to be proven. Good. So as I said, I'm not going to go into the details of the proof of this, but it helps me convince you that all the maps we've seen thus far certainly have all the properties I just described. So, for example, the non-selective measurement map I showed you, where you do a von Neumann projection and then you sum over k because you don't know which outcome occurred. Well, that's clearly of this form because the AKs are just the pi k's. The Hermitian adjoint of this guy is itself, so Hermitian operators. And if I summed over k, pi k, well, pi k squared is just pi k, sum over k pi k, well, that's identity because it was a projection value measure. So that has the crux form. If I look at the case of a mixture of unitaries, well, here it's not quite in that form, but I just massage it a little bit, square root of pi here, square root of pi here, and now I recognize this as the adjoint of this. So the AKs are just these operators. And if I take the sum over I, AK dagger, or sum over k, AK dagger, AK, well, the UI dagger, UI just becomes identity because it's unitary. So, and the sum over I, PI just becomes 1. So I have 1 times identity, I satisfy that. And this guy here is a little bit trickier to see, but let me do a simple example. Suppose remember, this is the state of the ancilla you've prepared, and then you're interacting the system and the ancilla by some unitary tracing over the ancilla. Let's imagine that the state of the ancilla you prepared is a pure state. Okay, so some projector onto what I'll call phi a. So I plug that in here, and now I can rewrite this equation by moving the phi a to the left of the system operator here. And I write out an explicit expression for the trace over A. So these J's are complete orthonormal basis for the A Hilbert space. And now I've got it looking a lot like that. This here is an operator on S and A, and then I'm taking this partial inner product on the A space from the left and from the right, and I'm going to get an operator on S. But because these aren't the same operator, this needn't be a Hermitian operator, but it's some operator on S. And similarly, this is some operator on S, which you can easily see is just the adjoint of that guy. So this one also has that cross form that I talked about. And so because of that representation theorem, it's clear that all of these guys are completely positive, not just positive, which is exactly what we'd expect. Because they seem like perfectly reasonable physical transformations that won't take a positive operator to a non-positive operator. So this is to give you a flavor for all of the things there are in space of transformations beyond unitaries. So this is the result I mentioned, that if you ask, well, what about an arbitrary map I write down? I just come up with a map, and I find that it is completely positive and trace preserving and linear. Does it follow that I can go to the lab and find some way of constructing a device that will implement that precise map? It turns out the answer is yes. You can always implement any map in this sort of way. You can always find a unitary coupling to some ancilla and a state for that ancilla such that you implement any map you like. It turns out that the ancilla has to have dimension at least, it has to have dimension the square of the dimensionality of this system. That's sufficient. And sometimes for certain maps it could be a smaller dimensionality suffices. But for an arbitrary map, a D, if this is dimension D, then a D squared dimensional ancilla will always suffice for implementing that map. So that's quite nice. Now we have these representation theorems for the preparations, the measurements, and the transformations. So for the preparations, I said, oh, any density operator? You can get that by a mixture of pure states, or by taking the reduced density operator for some entangled state. Either way, you can get any density operator. And for POVM, what we saw was that it's always possible to get, for an arbitrary POVM, to find a measurement that implements it by doing this thing where you couple to an ancilla and you measure a pair. And now we've found the same thing for these transformations. Okay, let me make one other point about these guys. And this will remind you of the discussion we had about the ambiguity of, or I'll say it this way, the fact that there are many pure state ensembles that give you the same average density operator. So here I want to convince you that there are actually many ways of implementing the same completely positive trace preserving map. So here's an example. So take this map, which is a mixture of the identity unitary and the unitary, which is just Pauli sigma z. So I can write it this way: it's a half identity rho identity and a half sigma z rho sigma z. This is really just U, rho, U dagger, but for the poly unitaries, they happen to be Hermitian, so U dagger is just U. So this is just a plain convex sum of two unitaries. And if you ask, well, what does it look like on the block sphere? So here's the block sphere. So say I have some arbitrary state lying inside the block sphere. The identity obviously just leaves it alone. The sigma z unitary rotates around the z-axis by 180 degrees. Because it changes the sign between the z up and the z down state. So, a state like the plus eigenstate of sigma x is a 1/2 up along z, down, and 1/2 down along z. And if I change the sign of down along z, I've moved over to down along the x-axis. So this transformation rotates you by 180 degrees. So we take this point here over to a point on the other side. And then it tells me to average those guys. And so that would land me, as you saw in the tutorial, halfway between those two, which means just project down onto the axis of the block sphere. And this is true for every point on the block sphere. Under that transformation, it gets mapped to whatever latitude it was at on the block sphere onto the central axis. So you can actually represent, for qubits, any completely positive trace preserving map as the image of the surface of the sphere under that map. And so in this case, the image of the surface of the sphere is just this guy here. So everything just moves into the central axis. Okay, so that's obviously not a unitary, because in this picture, a unitary just rotates all the points on the surface of the block sphere. And it tends to take pure states to mixed states. So, here are two pure states that it doesn't influence, the eigenstates of Z. It just acts like identity on those guys. But every other state decreases in purity because it gets mapped onto this central axis. Okay, so here's my question to you. What's a completely different way of implementing exactly the same transformation? Yes?
Measurement of the Z spin?
Exactly. If you measure the Z spin of the system, so here I'll denote the Z spin up and the Z spin down eigenstates just in that quantum information notation 0 and 1. If you do that and you don't register the outcome, so you know Z spin was measured but you don't know what outcome was achieved, then this is what our prescription was for the uptake map. I'm projecting onto the state 0, that's for the first outcome, and I project onto state 1 for the second outcome. And so I can just rewrite that as the final state is a mixture of the Z up and Z down eigenstates with weights corresponding to the probability that rho assigns to 0 and 1. But the probability that rho assigns to 0 and 1 just tells me where I am along this axis. And so that formula just describes, if I have some arbitrary rho, that formula at the bottom just tells me, it describes this state here, which has the same expectation value of Z spin as rho does, but now it's an incoherent mixture of 0 and 1. And as you saw in the tutorial, all the mixtures of 2 points on the block sphere lie on the line between them. And so that's exactly the same transformation. So this is a lot. This is very similar to how for a mixed density operator, there's these two radically different ways of preparing it. One is mix a set of pure states. The other is take the reduction on a tangled state. Here we have two radically different ways of implementing a given transformation: mixture of unitaries or some measurement whose outcome you ignore. You should have noticed a pattern that every time we define these sort of general classes of objects in quantum theory that describe preparations, measurements, and transformations, we tend to find this sort of ambiguity in ways of implementing them in mathematical decompositions. So here it's an ambiguity in the Krauss decomposition. These are both valid Krauss decompositions of the same map. I didn't say that explicitly, but there's no uniqueness to the Krauss decompositions. There's actually an infinite number of different Krauss decompositions for a given map. And it turns out wherever we see these kinds of ambiguities, we see them all over, we're going to see next week that there's a sense in which you get something non-classical in each of these cases. The fact that there's many different ways of thinking about how to implement a given density operator or a given POVM or a given CP map means that there are many contexts for that experimental procedure. And what we're going to find next week is that if you want a hidden variable model wherein you sort of imagine what's going on as some system with properties which is prepared according to some distribution, transformations might change those properties, possibly probabilistically and so on, you might have hoped that this context here, which doesn't have any effect on any of the statistics, right? Because, for example, whether I do this or whether I do this, if these are both black boxes and you are allowed to do any preparation and any measurement on either side, you'll never be able to tell whether it's this box or this box. Because the map is exactly the same, and it's all that matters for calculating the statistics, things down the road. So you might have hoped that because you can't tell the difference between what's in these two boxes, that the reason for that is that at the hidden variable level, they're doing exactly the same thing. They're maybe randomizing the hidden variables in exactly the same way. And then what we're going to see is that you can't have that sort of interpretation. So whereas your statistics in quantum mechanics don't depend on these contextual differences, any hidden variable model is going to depend on those sorts of differences. Yes?
You mentioned the multiplicity related to maps and related to preparation procedures. Is there a similar multiplicity related to measurements that?
Yes. So yeah, I think I didn't say it explicitly, but we did see two ways of implementing a POVM. One was a mixture of projection value measures, and the other was couple the system to an ancilla and measure those guys. So I can give you examples of POVMs which can be implemented in either one of those ways. So that would be an example of a non-uniqueness of the way of implementing a POVM. Anyhow, so that's just kind of a note for what's coming next week. Okay, so now I only have a bit more to tell you about the general operational framework. So let me take stock of that for a bit. So now we have the most general form for representing preparation, transformation, and measurement. The general form of the Born rule is if you tell me what you've done, what preparation, transformation, and measurement you've done, then I can predict the probabilities for the outcomes of that final measurement using this formula. Rho, map it forward by T, take the trace of POVM elements. Now, the same sort of things we saw, I think it was the day before yesterday, we can group that transformation together with the preparation if we like to define an effective preparation. It's just now I apply the map T to rho to get rho prime. And so then I see that this rule comes out as a special case of the old Born rule without transformations. But I can also, of course, lump it together with the measurement if I like. And so this is just like the Schrödinger and Heisenberg pictures, but now at the level of these more general transformations. And this may not be familiar to you, the idea of taking the adjoint of a map on operators. So let me say a few words about the Heisenberg representation for these CP maps. And these technical details will be useful later. So I want to define the adjoint of one of these maps. These maps are sometimes called superoperators. They map operators to operators. And I'm going to imagine that the set of operators we're interested in are the Hermitian operators. What's nice is that I can think of the set of Hermitian operators as forming a vector space. If you recall what the properties I have to have for a vector space are, well, one is that arbitrary linear combinations are also valid vectors. So if I take alpha A plus beta B, where A and B are Hermitian operators and alpha and beta are real numbers, I get another Hermitian operator. So they satisfy that property. If I multiply by any real scalar, I get another vector. So you can prove that they have the properties of a real vector space And on that real vector space, I can define an inner product. So this is my notation for the inner product between operator x and operator y. I define it just to be the trace of x times y. This is called the Hilbert-Schmidt inner product. Good. So now I can define the adjoint of one of these superoperators in exactly the same way as I define the adjoint on any vector space equipped with an inner product, which is just you say the adjoint of T is that map which, when acting on x and taking the inner product with y, gives me the same thing as x inner product with T acting on y for all x and y. Okay, and then according to this Hilbert-Schmidt inner product, that means that the adjoint of T is defined by the trace in this sort of way. And what it's not difficult to show is that if you know that some Krauss decomposition of that superoperator, then the adjoint is just obtained by putting the dagger on the leading AK and no dagger on the final AK. So the proof of that is pretty straightforward. So I'll use this formula here. So the trace of x times t acting on y, well, here's just the action of t. Pull the sum over k out. And now I use the cyclic property of the trace. Now, question, did you guys come across the cyclic property of the trace in Joseph's course?
Yep.
Yep, okay, good. So I can move the AK dagger over here. And now I'm acting what I wrote down for T dagger on X. And so now I've established this equality, so that is the correct expression for T dagger. Good, and as an example, just to sort of sanity check, if you say, well, what if this completely positive map is just a unitary map, U dagger? Well, sure enough, the Hermitian adjoint is just U dagger U, which we recognize to be, the appropriate Heisenberg picture representation of that unitary dynamics. That's how I would evolve measurement operators forward in the standard forms. Okay, so you again have the Schrodinger Heisenberg picture. Everything works out as you expect. Now there's only sort of one thing I haven't told you about that I haven't generalized. Can you tell me what it is? Is this a question or?
Yeah, question.
All right, give me the question.
On the previous slide,
Previous slide. Yeah.
in the sanity check,
Yeah.
were we assuming that without this information, or no, we weren't?
Assuming that, sorry, what?
So we weren't information conjugating all of T acting on dot. I'm not.
So here I'm saying this is a particular example of a completely positive trace preserving map. It's just a unitary map. And it corresponds to this kind of decomposition where there's only one term in the sum, and that one term, A is U. So A dagger is U dagger. And so then if I just say, okay, well, then this tells me how I should express it for the dagger map. It's just going to be U dagger.
Notation. That's right.
Okay, so what's the one thing I haven't told you how to generalize? Yep.
Collapse.
Right.
So everything is deterministic.
Exactly. So suppose, remember way back we said, well, if I have a measurement which has an output port, so the system survives, and I get to learn what the outcome K was. Well, then there's a map from your representation of this preparation to the representation of this effective preparation, which depends on K. And in the standard formulation, that's usually presented as the von Neumann projection postulate. Here, there's a much more general set of mathematical objects that can describe those sorts of update maps. And I'm not going to go into too much detail, but the update map, the most general form of update map looks like this. So the script tk of rho, that script tk is a completely positive linear map, just like the transformations we saw. But it doesn't have to preserve the trace. So it can't increase the trace, but it can decrease the trace. So it's a trace non-increasing completely positive linear map. And the idea is that the trace actually of the final state, tk acting on rho, so this expression in the denominator, that actually tells you the probability that outcome k occurred. And because different outcomes can occur with non-zero probability, and they don't all occur with probability 1, that's why this thing is not trace preserving. And if you tell me that this guy here, this measurement, is associated with the POVM with elements EK, how does that constrain these maps here? Well, it turns out the adjoint of TK, acting on the identity operator, gives me the kth element of the POVM. The connection with what I just said about probabilities will follow from the definition of the adjoint right here. So I said that the probability of outcome K is trace of TK of rho. But now I can write this as an inner product between identity and TK of rho. Right, so throwing an identity in there doesn't matter. And then I can just move this TK onto the identity, but turn it into the adjoint. So, and I know that this probability of K is also expressed as trace of the POVM element EK times rho. And so if this equality holds for all rho, then because rho is a basis of the vector space of operators, of permutation operators, I can infer that these two guys must be the same operator. So this isn't going to be so critical for the rest of the course, but I thought it would be nice for you to see kind of the complete picture. I don't expect you to really kind of get what's going on here without seeing some interesting examples. But I thought I would just sort of tell you the overall picture, so you know how it all fits together. Well, let me say a few more things about this. So if you say, well, what are the mathematical properties that those script TK maps have to satisfy? Well, they also should be convex linear, because if I'm mapping some state rho I to TK rho I, so I know K, I know what the output state is. But whatever knowledge I had about the initial state, whatever ignorance I have the same ignorance about the final state. I know it's some probabilistic mixture of every one of the initial states mapped forward. So it should be convex linear. It should be trace non-increasing because of this fact that the trace gives me the probabilities of those outcomes. And of course, it should be both positive and it should be completely positive because, again, I can act this conditional transformation on half of an entangled state. If you ask, well, what about a Krauss decomposition? You find that the only difference, it also has a representation theorem. So now these A's are going to be labeled by K because the map itself is labeled by K. So I've changed this index to be mu. These A mu's are, again, arbitrary linear operators. But now instead of them having to sum up to identity, they just sum up to EK for the measurement that has POVM elements EK. And it's easy to infer that from the equation that we have over here, because remember, TK dagger is the one where I sum over mu, A mu dagger, rho, A mu. But if I'm mapping it on identity, that just becomes this guy here. Okay, so it's a slightly broader set of transformations. And now you can see that the old familiar von Neumann projection postulate becomes an example of this sort of guy. So the numerator is the TK of rho, like we had back here, right? It's just the numerator that's TK of rho. And in this example, it's just pi k rho pi k. So that's what the A mu's are. And sure enough, if I look at just pi k squared, well, that's just pi k, which is the kth element in the projection value measure. So this is a particular example of one of these update maps. You might ask, well, what if we're doing something that's not a projective measurement? What kinds of update maps do we find there? So I should emphasize that whereas your textbooks might have left you with the impression that measurements always update by this von Neumann rule, in this operational framework, that's not correct. That there are many, many ways that the state could update, even for a projective value measure. It's not always this von Neumann update map. And so this is just one way that things could update according to this measurement. And this is just one way that people have considered about the way states can update under a POBM. And it's basically to conjugate rho with the square root of the POBM elements. So if you compare it to these expressions up here, square root times square root will give me the POBM element. And alternative ways you could do it would be, for instance, suppose I'm doing a projector measurement. After the measurement's done, I apply a unitary to the final state before it comes out of the box. And that unitary depends on the outcome. I could do that. I could set the box up like that. And then this form would change from this to a situation where I have a UK here and a UK dagger here. And that wouldn't be the von Neumann projection postulate, but it would be a perfectly good way, a perfectly good update map. So the actual update map you use cannot be inferred from the POBM. There's a one-to-many relationship between the POBM that describes the measurement and the set of maps which describe how it transforms the state. So that's something important to bear in mind, that I think this is something where the textbooks kind of make us have the wrong intuitions. Von Neumann update is all there is. There's many ways you could update for a given measurement. One other comment I'll make is that in comparing the kinds of update maps you have for projection value measures and the kinds of updates you have for positive operator value measures, there's a difference about repeatability. With this kind of update map, if I project into the kth eigenspace, and then I do the measurement immediately again, well, I'm going to get the kth outcome again, because now the state lies in the kth eigenspace. I'll definitely get the kth outcome. But with these kinds of maps, typically you'll find that you can get a particular outcome, and even though you repeat the measurement immediately afterwards, you can now get a different outcome. So these tend not to be repeatable. That's one way of trying to pick out what's special about the projection value measures among the set of all POBMs. They're the ones for which the outcome is repeatable. The outcome will be reproduced if you repeat the measurement. Okay, questions about this? Again, it's really not critical for the rest of the course, but I thought it's useful to sort of see the whole picture. This is kind of especially in quantum information theory, this is how we think about quantum mechanics. This is its most general formulation.
So given a POBM or PBM, how do you decide what the update map?
It's not meaningful to ask what's the update map if I just tell you what the PEVM is. I have to tell you more. So if I have just done an experiment in my lab, and I say, what I can tell you about it is that it's represented by this POVM, you can't say what update map is. You have to say, well, tell me the details of how you did it. Then you can figure out what the update map is. So all you know is that the update map is constrained. Once I tell you the POVM, you say, well, out of all the sets of trace non-increasing completely positive maps, it's only those that satisfy this identity that are viable.
So what other details do you need to completely specify?
Well, for example, do I have an example here? No. In this case here, if I had a mechanism inside the box which looked at the outcome and then did a unitary on the system depending on that outcome, that would mean that it was a different update map from this one, even though both of them are represented by the same projected value measure. Because if I have a UK and a UK dagger, and then I take this expression, well, the UK dagger, UK cancel, so it still corresponds to the same projectors. And so now I'm describing what's going on inside the box.
In this case, for example, what are the details of the measurement that give these examples?
So I'm not exactly sure how to answer your question. What are the details? Let me try to answer it. I'm not sure I'll do a good job, but the POVM you associate with the measurement, it's in the service of predicting the outcomes you get for that measurement. And also sometimes it's in the service of trying to figure out what happened before, like what preparation was done. So in the case of like quantum communication, I put one of several quantum states into a channel, try to encode some message, send them to you, you do a measurement, and based on the outcome, you try to figure out which message I've encoded. So you can think of it as, POVMs are really about retrodiction, finding out more information about what happened earlier. These update maps are about predicting the outcomes of other measurements down the road. So I've done a measurement here, got an outcome, and now I want to predict what's going to happen down the road. So there's facts about what I've done in the lab that are relevant to what's going to happen down the road, but totally irrelevant to my retrodictions about the past. And that's why telling you how I'm going to retrodict the past may not be enough for making predictions about what's happening down the road. Does that help? Sort of? Okay. Other questions?
Can I just ask a quick question? I think I missed it just now.
Yeah.
Where do you get the first line of that?
Yeah. Here?
Yes. The very first line.
Yes.
So how do you get the equality?
How do you understand the first line?
Yes. So you started with that, and then you showed that,
Right.
yeah, the adjoint of the identity has to be PK. But how do you get the first line?
I guess it's sort of by definition. I define these TK maps to be those maps which take a given density operator to the unnormalized final density operator. So the final state times the probability with which it occurs.
Right, but why should that give you the... Well, I mean, if you take a trace of that, why should that give you the probability of K?
Well, so if my assumption is that TKs are defined as mapping rho to the final state, we call that final state rho K, times the probability with which it occurs. So TK of rho is going to be the probability of K times the final state rho K. Okay, that's my definition. Now, if I take the trace of both sides of this equation, I just get probability of K times trace of some normalized density operator, which is 1. And so I derive the first line there. Is that clear?
Right, okay.
So it's really part of the definition of these maps. Other questions? Yes.
So you're saying that the update rule depends on what we've done in preparatory stage, right? So couldn't I just say I should have been updating my state throughout the preparatory stage and using the same update rule at each point?
Did I say that the update rule depends on how you prepare the state?
You have to know what we've done. Perhaps I'm
So I guess,
translating that wrong.
yeah, I would want to say that, let me sort of find the right bit here. So these maps here really depend only on the list of instructions that would have done here. So you can think of these maps as taking you from a description of this preparation to a description of this preparation, but they're only a function of what's going on here. Because for every different choice of preparation here, all that influences is the row that I'm feeding into the map. It doesn't influence the parameters in the map itself. So these maps really are just a description of the measurement procedure.
Okay, but then you said if we do something that transforms our state by a unitary, then we end up using a different different update rule on the next slide.
Yes,
PDF.
yes.
So what kind of operation are we doing then? Are we doing an operation of unitary within the measurement box?
Yeah, exactly. So I was imagining that suppose we open this up and we see not the standard way of doing objective measurement, but a fancy mechanism that first does the measurement and then has sort of an automation which says, well, if the outcome's 1, then I'll apply this unitary. If the outcome's 2, I'll apply this unitary. All in some sort of just automated way. Well, then that's a perfectly good measurement, that whole mechanism. And I can ask, well, what set of maps should I use to describe it? And I'll find that for that kind of business, it's not this standard thing, but rather one where I have a UK and a UK dagger here for some set of images. But yeah, it's all happening inside the box.
Couldn't you say that, okay, this thing that applied one unitary given one case and a different unitary given another case was the measurement, and then the unitary was an evolution on my updated state?
You could. I mean, you can certainly parse things as you like. And we've been doing that back here, where we sort of said, well, I can think of this as part of a measurement. I can think of it as part of a preparation. And so my comments about that final unitary, certainly you could say, what comes out of my measurement box here could be not just a quantum system but another system which carries information about K. And those two systems go into a transformation, which gives you sort of a UK, it's a unitary on the system that depends on K. And I want to think of that, I want to parse them as measurement followed by transformation. You can do that. But of course, your definition of the system would have to change so that the information about K could get propagated. And so it's just your choice. How do you want to describe that? But if you ask the question, imagine a box that has anything at all inside, no constraints on what you put inside. What sorts of maps do I need to describe that full set of possibilities? Well, you find that the projection postulate is not enough. You need these more general sorts of things, because you could always parse it in the way that I described. All right, look at the time. Good, so I think we won't get to axiomatization today, but we're sort of all set to go. Let me just skip that. Actually, it'll take you just a few seconds. I just think this is really curious. I don't know if it'll be good for any of you, but I remember way back when I was only familiar with the textbook formulation of quantum theory, and I didn't know anything about completely positive maps. It puzzled me that in my textbooks on quantum optics and field theory, they told me that the way a state updates when you measure, let's say I've got like a mode of an electromagnetic field, and then I put a photodetector on it, and I find a photon. And the textbooks told me, oh, you annihilate a photon from the state, and then the new state is the normalized version of this annihilation operator state. And I always thought, well, that looks nothing like the projection postulate, because A is not a projector. What's going on? Well, this is just a perfectly good example of a Krauss decomposition of a completely positive trace non-increasing linear map. So that sort of incongruity is resolved by this more general framework. So if you've never seen this, then it won't have puzzled you, but maybe you have, and now you know how it's connected. So anyways, this is where we ended up. We now have reformulated those textbook axioms to a set that make no mention of physical states or their properties or how those evolve in time. Instead, we just say, we make statements about preparation procedures, measurement procedures, and transformation procedures. So every preparation is associated with a density operator on a complex Hilbert space. Every measurement is associated with a positive operator valued measure, and the probability of that measurement yielding outcome K is given by this form relation. Every transformation is associated with a trace-preserving, completely positive linear map, not necessarily unitary. And finally, every measurement outcome K is associated with some trace non-increasing, completely positive linear map that satisfies this definition, and it can be more general than the projection postulate. So what's great about having the axioms in this form is that now we have a kind of a minimal interpretation of quantum theory. We don't have to talk about the physical properties of any system. So in a way, this is very conservative, and we can reason using this framework without necessarily being worried about bringing some realist preconceptions that are classical and inappropriate. So this is a very safe place in which to do physics, and most of the quantum information community thinks about quantum mechanics in this sort of operational way, just to figure out cryptographic protocols and all those sorts of things. But the second thing is that if we want to try to locate quantum theory in a space of possible ways the world could have been, we now have a target. We can say, well, at the very least, we should derive quantum theory in its operational form. Because we know whatever more interpretive structure we can put on it, we know that at the very least, quantum theory makes these kinds of predictions. And so if I can come up with a set of axioms that at least rederive this, then I might learn something about what the underlying principles of quantum theory are. And that's where we're going to go next time. I'm going to say a little bit about axioms that get you some of the structure.